Hello, this is a presentation on the Sieve of Eratosthenes. So, the Sieve of Eratosthenes is an algorithm which aims to identify all the prime numbers in a segment of n numbers efficiently. We can further use this in a hash set to quickly identify prime numbers less than n in constant time. The algorithm is very simple. At the beginning, we write down all the numbers between 2 and n. We mark all proper multiples of 2, since 2 is the smallest prime number, as composite. A proper multiple of a number x is a number greater than x and divisible by x. Then we find the next number that hasn't been marked as composite, which is in this case 3, which means 3 is prime, and we mark all proper multiples of 3 as composite. The next unmarked number is 5, and we keep going on in this way. So the idea behind this is a number is prime if none of the smaller prime numbers divide it. Since we iterate over the prime numbers in order, we already marked all numbers who are divisible by at least one of the prime numbers as divisible. Hence, if we reach a cell and it is not marked, then it isn't divisible by any smaller prime number and therefore has to be prime. So we just implement this algorithm in code, which is we're using C++. We're using two simple for loops for this. So basically the first code, which just marks all numbers except 0 and 1 as potential prime numbers, and then it keeps going through this process. For this, it iterates over all numbers from 2 to n. If the current number I is a prime number, it marks all numbers that are multiples of I as composite numbers from I square and so on. This is already an optimization over the naive way of implementing it and is allowed as all smaller numbers that are multiples of I necessarily also have a prime factor which is less than I. So all of them were already shifted earlier. Since I square can easily overflow the type int, if you notice the additional verification is done using type long before the second nested loop, as in the code. So the interesting part of the algorithm is that it runs an O of n log of n. It's simple to prove a running time of O n log n, ignoring the is prime check in the code in the third line, is prime check. The inner loop runs at most n by I times for I is equal to 2, 3, 4, etc., leading your total number of operations to be n into 1 by 2 plus 1 by 3 plus 1 by 4, which is harmonic series. So it's bounded by log of n. So whole thing is n log n. The algorithm will perform n by p operations for every prime number p that is less than or equal to n in the inner loop. Hence, we need to evaluate the next expression. The asymptotic analysis is the summation of n by p is equal to n summation 1 by p, where p is prime. So the number of primes less than or equal to n is n by log n. So when we extract the first prime number 2 from the sum because it makes the denominator go 0, k, if k is equal to 1. We now evaluate this using an integral, which is a valid approximation using the rectangle method. The integral, which as is shown here, this integral evaluates to log n because 1 by k log k dk, so that evaluates to log n. Using substitution and removing terms of lower order, we get log of log n minus log n, which is, according in time complexity terms, it is log n. So if we return to the original sum, the whole sum n by p summation is n log n plus O of n. So like the more strict proof is in the book authored by Hardy and Wright, which is an introduction to theory of numbers. It's a really great book. So we also use the sieve of numbers, which means we store all the numbers in memory. This also implies that it needs O of n order of memory to work, as opposed to the general O of 1 for most prime number calculators. The are kind of some optimizations. So the biggest weakness of the algorithm is that it keeps walking along the memory multiple times while only manipulating single elements. This is not very cache friendly due to the many cache misses, and because of that, the constant which is concealed in the O n log n is comparatively big. Besides, the consumed memory is a bottleneck for big N. So a few potential optimizations are sieving till the root and not till the main number, because if you want to find all prime numbers till n, we only need to check till root n. And sieving by odd numbers only, which is it's a linear speed up, but we can just stop checking for even numbers after 2. The last one is using efficient structure. The Boolean vector implementation we used in the code had an optimization which made it take only n by 8 bytes of memory instead of n, which could be useful. Modern computers are actually way faster at accessing bytes of data, which could potentially increase time taken. However, for simple sieve algorithms, vector bool performs faster because there's a smaller size of data which can be cached efficiently. Thank you for listening to our presentation.